Hello everyone, welcome to Analog Circuit Design. This is lecture 4 recording. We're talking about MOSFET operation, and I'm Teo Kang. I would like to acknowledge Michael Flynn, my advisor, and then also I want to acknowledge Dr. Sung-Jong Lee, who is a friend of mine. And again, the textbook is Design of Analog CMOS Integrity Circuits. This slide shows our class status. So far in the week one, what we did is introduction and basic circuit theory like Norton and Thevenin, and we also cover some MOSFET basics like how MOSFET looks like, how does it work. And today, this lecture, which is lecture 4, week 2, we'll learn about MOSFET operation region. There's total 3 operation region. We will cover that, and then we'll also cover some equations about that, like current equation. And next, we will cover some second order effect. These are like side effects, you can say. These effects are usually not desired for a circuit design. And we'll see. We'll see how we can cover this. If there's too many things, and then maybe we can just remove some of the like less important thing. Well, we'll see. Here's the outline. We're going to talk about MOSFET basics, structure and operating region. This is really important. This is really important thing. And then we'll talk about lots of side order effects. And then also we will have a glimpse on layout and also parasitic capacitance. Let's talk about MOSFET operation region. There are 3 regions: cutoff, when the transistor is turned off, and here triode, and when the VDS is not enough, like VDS is not high enough, then we're at triode region, and when VDS is high enough, then we're in saturation region. These 3 are really important when you design circuit. For example, whenever we design, let's say, amplifier, then at the very beginning phase, what we do is that we check every MOSFET's operation region. So it depends. Of course, we're not using cutoff region for like normal circuit design, but we both use triode and saturation region. Well, mostly saturation, but these 2 are like kind of common. Let's talk more about operation region. So here's a schematic. Here is a schematic, and then the source is connected to ground, and drain. The voltage of drain is changing, but this voltage is also referred to ground. So when we change the voltage source, it means this is directly the VDS. So VDS is the voltage between drain and source, and we have VGS. VGS is voltage between gate and source. So cutoff, this is when MOS is off. VDS doesn't matter. It just when VGS is too low, then the transistor is not turned on. So it's cutoff is kind of turned off region. And next, again, triode. So when you see the graph, what it means is VDS. So this gray marked area is triode region. So it means that VDS is not high enough. So basically MOSFET is turned on. So VGS, which means VGS is still higher than certain voltage, which is the subthreshold voltage. So in triode region, MOS is on because VGS is high enough, but VDS is low. That's where we define triode region. So when you see the graph, for example, let's say, so the graph shows that there's 3 variation of VGS. So VGS1 graph, and VGS2 and VGS3. So, and then you can see that VGS1 is the smallest, and VGS2 is after that, and the VGS3 is the largest. So if VGS is like become larger, the current become larger, right? Because it turns on the switch stronger. But we'll cover the equation later in the lecture, but at this moment just get a intuition that if we increase the voltage of VGS, then current flows like more. So you see that VGS1 has the lowest current, and then VGS2 has the like larger current. But what it means is that when you see, so x-axis is VDS. So here, with a fixed VGS1, if we increase VDS, so, and then the current is increasing, right? And then right before VDS is less than this point, then the gray area, we call this as triode. So what it means is if the VDS is larger than this one, then it becomes saturation region. So in this graph, these kind of dotted line doesn't mean anything. Only the solid line with gray area is what we call triad region. So this is very important. Very important. I think if you're still confused, then turn off the video and then try to get this like concept. I know because there's multiple VGS and then VDS, it's kind of confusing, but understanding this graph is really important for today's lecture and circuit design. And then the third saturation region, it's opposite. In triad region, VDS was low, but in here, it doesn't matter about VGS. Well, still VGS should be turned on. I mean, higher enough to turn on the MOSFET. But the point here is that with a given VGS, if VDS is large enough, then we call it as saturation region. And then maybe with some just like a rough look, what you see here is that the current is not changing that much, right? What it means, so let's see the VGS1, this graph. So if VGS is fixed for this graph, because you see that there's VGS1, so this graph is, the VGS is fixed. And then even if we increase the VDS from here, current is not increasing that much. So when you see, when we come back to this circuit, it's kind of weird, right? Because if MOSFET is just a kind of transistor, I mean resistor, assuming that MOS kind of just resistor, if we, and then we're fixing VGS voltage here too. So if everything is fixed, and then if we increase VDS, then just intuitively ID should increase, right? But it's not increasing. Well, it increased, but it's not like it's not intense, tends to increase. So that's a key point here in saturation region. Even if we try to increase VDS, the current is not increasing that much. So this is also very important. In this slide, I think this slide is kind of the key point of today's lecture. So please repeat it to fully get the saturation region. I mean, draw. Here's a lemma of current definition. This is from textbook. What it said is, so what is current basically? Current is I here. So current is a movement of charge. Yes, actually the movement of charge. So charge times velocity. So current is like, right, for example, I think a lot of people just use metaphor as a car movement in like highway. If so, as current is kind of how many cars passing by a certain line. For example, like in a high pass or something, you can kind of count how many cars pass by, right? So there's multiple ways that we can have car, I mean the number of cars. So here, so the highway is assuming that highway is here, and then we're counting car at this point, and then car is just moving around, right? And then car is going here. So current is kind of how many car pass this line at at some certain period of time. So how can you increase the number of car? There's two way. First, increase the number of car. I mean, just pack it. Just pack this area with car, and then if this car pass this line, then well, counting car, cars, a lot of cars are passing by, so we say there's a lot of car. But in current, this can be just electrons. So if there's many electrons, then we have higher current, which then that corresponds to this Q charge. But there's the other way to increase the current, to have higher current, right? Just assuming that there's few electrons, or let's say car. If we make these electrons move very fast, like they go very fast, we can still we can still achieve high current, which means that's the voltage. So either packed the highway with car or make them move faster. So that's how we get kind of current. Now let's do some math. We're gonna calculate the current in triad region MOSFET. So we'll start from the current lemma. Current equal Q, which is charge per unit length, times V, velocity. So first, we want to calculate charge per unit length. What it means is that from here to here. So it's a function of x. So in every x, they have their own charge charge per unit length. So the way how we calculate is, so we're kind of looking at the slice here, this slice, you see. So what we're doing is here, each slice, okay? So first, W. There's W coming because W is this. So just think about it. If W is larger, of course, there more charge, right? Because you see, we are calculating this each slide, but if W is large, then there will be more charge, right? So we're going to multiply with W, and then next COX. This is kind of a oxide charge, the number. It's kind of a like density, and then in this part, we need to understand where this part comes from. So, do you remember in previous, I think it's in a previous lecture, inversion layer happens only when VGS is higher than VTH. So here, when we see here, so we're calculating actually the channel charge. So channel. So channel only happens as start to appears when VGS is higher than VTH, and after that, the charge is kind of proportional to increase of VGS. So we have to substitute this VTH when we calculate charge, and then this part minus Vx. That's because in source, the voltage here is 0. So the voltage here is 0, and then drain voltage is higher because this is NMOS. And then Vx means the voltage at X. So if we put 0, X0, that means voltage is 0, which means they have more charge. This part can be confusing, but let me explain it again. So again, we are substituting this VTH because the channel appears when VGS is higher than VTH. And then we are substituting this Vx because we're substituting this Vx because when we put x 0, that means so V0 is 0, right? Which is at this point. And then the charge, because of the voltage across source and drain, the charge kind of density is the highest at the very beginning. So that's what it means. So when Vx is, if we increase x, this goes here, Vx is kind of increasing because we apply some drain voltage here. So the way how we can understand it here is that at the source, since the source voltage is 0, it will have more charge. And here, this is what they show. So actually, this one corresponds to this. So if it's closer to source, where the source is connected to 0, it has more voltage difference, and then that will give us more charge. I think you guys already know about this, but do you know about Q equal CV? Capacitance times voltage. Well, actually, this is it. So this is capacitance and this is voltage. So that's why we kind of calculating in this way. So Q equals CV. Okay, so we calculate the QD. And then note that this is not like fixed number over X. X means the length, the position between source and drain. So this is not a fixed number. This QD is changing over the position. And because we have Vx, because Vx is, you see that here's a voltage difference, they are changing, so that's why QD is not a fixed number. QD changes over the position. Okay, let's come back to, let's calculate I. So we calculate QD. Just put it here. Just this polarity, that's fine, it doesn't matter. But from the notation, we just put it minus in here. That's okay. And we need this velocity, right? So velocity is here. And then actually velocities can be represented with this equation, which is mu is a mobility of carrier. In our case, this is n mass. What is the carrier? Electron. So this is a mobility of electron. And then the E, the like a electrical field, is a function of a derivative of V. So we're going to put this equation to here. And then this V is, you say, see, the same V with this. So gate sub voltage difference, that's V. Okay, let's do some more math. There's tons of equation. So we just substitute this V to here, and then we got this equation. And then what we're going to do is we will integrate it from x0 to L, so 0 to L in both sides. The reason why we are doing it, because we don't want this kind of position dependent value. We don't want that. We just want a constant, like a single scalar value current. So, I mean, this is, from this equation, this is fine, right? We can just integrate it over x. Here, integrate over x, but here, because this is a function of v, and then, so it's actually, there's dx, so we kind of move it to here by multiply, and then put this integration here, right? And then, so we're integrating over x or v. Over x means we're integrating from position 0 to here. So that's what we're having. and in what corresponds to this X position will be the voltage like boundary condition. At V0, that's 0. And with VL here, that's VDS. So we're going to use that value for this integration. But here, the good point, like a good news, is that ID, the current is always constant because current is flowing from here to there, right? This is a current flow. So there's a law of like, what's it, charge preservation, or maybe even KCL. But anyway, the point is the flow current is always constant through this area, because if it is not, then current means keep increasing and maybe keep decreasing. That cannot happen, right? This is kind of a very basic law of current. So I hope you guys are already familiar with this. So anyway, current from here to here is constant, so this will just go to LID because current is constant. And then if you do calculation here, so if you do like, this is kind of a simple calculation, you know, this can be just 1/2 VDS square. I mean V square, it's not VDS, just V square. And then just do calculation, very simple. And then finally we got this equation. So now we got this equation. I think that's okay. You don't have to remember all the things, but I think what we can get from here is that like how actually we calculate the current. Like for example here, we calculate the current starting from this current lemma, and then the other point would be, oh, the voltage here is not a constant, so we kind of need to take care of that voltage change from drain to source. So those kind of key concept is what we really need, because when we do circuit design, we're not like deriving this equation all the time. I mean, it's been a while for me to see this again, but let's just understand the basic concept. And this equation, I suggest you to remember. We're gonna use this equation a lot. So yeah, let's just remember this equation. After a lot of math, we got an equation for triode region MOSFET current. But there is a problem. Well, it's not a problem, but like this equation cannot cover everything. This is only correct for linear region. So what this graph shows is that if we plot this graph over VDS, then actually the graph will be like this. Like, just forget about this VGS1, VGS2. Let's just focus on VGS3. So this VGS3, this graph is what corresponds to this equation. If we just blindly plot the current profile over VDS, this is how it looks like. And then here's some weird thing happen. It's how can the current, like this part, how can the current decrease if VDS increases? Here, we increase VDS, and it seems like the current should increase, right? Because I think we already talked before, it's like increasing the voltage over 2 points, 2 ports. So in like with common sense, if you increase VDS, it seems like the current should increase, but here it's not. Current is decreasing. That's wrong, right? Again, let me just brought it again. So here is source, and here is drain, and here is gate. What I'm saying is the current flow here, if we increase VDS, which means if we increase the voltage here, current should increase, or at least it shouldn't decrease, right? So what it means, this equation is not true when VDS is like large. So this part is not true. I'm saying this part, we can't use it. This is wrong. This is wrong equation. So we need different equation for that region. That's the saturation region. That's where the saturation region starts. So here, this point, saturation region starts. This point, saturation region starts. This point. And then again, the difference between these three are the different VGS. So basically, they're just, I mean, they share the same like mechanism. So again, as we said before, only this part is what that triode region current can cover. So we need a new equation for this part, right? We need a new equation for this part. And it turns out it actually looks like this. So current is not decreasing like here. Current is actually kind of increasing, but not that much increasing. We'll talk about that too. So this is what we kind of can guess how it looks like. Well, actually, this is how it looks like, and then this it kind of makes sense, right? So the current, it means we say current saturates after the peak point. That's why we call it a saturation region. Even if we increase VDS, the current is not like increasing much. So we say current is kind of saturated. But again, current is not decreasing at least, so it's kind of makes sense. And then we'll dig more into this area because this is a really important area. Most of the every analog circuit kind of use the MOSFET in saturation region. We'll learn that about like later lecture, but anyway, the point is saturation region is really important. This is what happened in saturation region. In when Vx, when VDS, actually VDS is equal to VGS minus VTH, it becomes, at this point, there's no like channel. So it's the channel draw like this triangle shape. And at this point, channel disappeared. And then we call this as pinch off. So at saturation, like at the edge of saturation, pinch off happens. That's what we call, that's where saturation region starts. And then, because what we want to know, what we're interested in is that why it is saturated. I mean, why current is saturated? Why current isn't going up with increasing VDS? That's what we want to know, right? And then that's why we call this a saturated. The reason is that the amount of channel, the charge here is decided by this VGS voltage. But we're not changing VGS, right? We are just fixing this VG voltage here. So with limited number of charge, and if we increase VDS, so here, this pinch off point moves to left. So what happens here is that we kind of have this empty space, which is depletion region, because this N plus becomes a more like positive, and then the depletion region is following here. So there's no channel. So this is what we have. And then the current isn't increasing. Well, actually current is increasing, but at this moment we'll just keep saying current isn't increasing. So current stays the same because of this limited charge channel charge amount. So what happened in equation? So this is a linear region equation, and then we substitute Vx as a VGS minus VTH, and then we got this square root of VGS minus VTH times this coefficient here. So this equation is a saturation region equation. This is really important. We have to remember it. This is used everywhere whenever we design This is a very basic equation. We have to remember it. And then you see there's L prime, YL prime. In the previous linear region equation, L was just L. So L means the length between channel source and drain. But here, since we have L prime, I mean pinch off, the channel length is actually decreased. So we're using L prime. L prime means decreased channel length. Can you get something? Can you get something here? Because L prime is keep decreasing while we're increasing VDS, then maybe current is increasing even though it is saturated region. Since the L prime is increasing, then maybe current is increasing, and that's true. Current is increasing actually. Even though it is in saturation region, if we increase VDS, current is increasing because of this effect. L effective is increasing. We'll talk about this later. That's a second order effect. But at this slide, let's focus on the saturation, meaning that the current is not increasing even if we increase VDS because we have limited charge in channel. Um, yeah, and then, but then you ask, what happened here? There's no channel. How can current flows? In this area, the velocity of electrons rises tremendously. So it's more like charge is moving here, and then at this area, just shoot through to the drain. So it's like, because electron is moving from here to here, right? You know, because the move of electron is opposite to current. So just remind that. So at this point, at this depletion region, just electron just shoot through. Um, and then in most of the case, we can just assume that L prime is almost equal to L. That's also kind of related, something like, that's also the reason why we kind of try to use long channel, but that's okay, forget about it. Um, we'll cover it later. So here again, let me summarize this slide. In saturation region, current saturates. Current saturates even though VDS increases. Because we have limited charge in channel, so even if we increase the VDS, they have kind of a limitation on flowing current. So because of pinch off. But in this empty space, current still can flow because of some tremendous velocity here. If you're interested in more about this, the detail, so the textbook also doesn't talk about this. Maybe it's in Wikipedia or whatever. Let me know if you're interested in. Maybe we can talk about it more. Let me just fix one thing in the previous recording. So this is actually VDS. We substitute VDS with this, not VX. And let's work some example. So here's NMOS VTH 0.5, PMOS VTH minus 0.5 volt. Well, I think we haven't covered PMOS, but they're basically the same. They're kind of the opposite polarity, but you'll figure it out. So there's three cases. Two of them are NMOS and one of them are PMOS. Calculate like VGS and VDS and then decide what region are they. Is it cutoff or is it triode or is it um, saturation? We'll check it at the in-person meeting, in-person class. So far, we talked about a linear region and saturation region and their equations. Now let's look at some example. First, can we use MOSFET in linear region? And then if it can, and how? Here, there's a resistor IV curve. This is what resistor is defined, the definition of resistor. If you increase voltage, proportionally increase current. So this is the NMOS current curve. This part is kind of saturation era, a region. But when we look at this very initial part where VDS is not high, which means triode region, I mean linear region. So when we um, zoom in here, these are kind of linear. And so x-axis is V and y-axis is I, so it's kind of a resistor, right? So it is a controlled resistor. Let's look into more about on the resistance of that linear region MOSFET. So here's a current equation for linear region. We learned it before. And assuming that VDS is really small, when VDS is really small, in this equation, we kind of can ignore this part because, I mean, if VDS is smaller than this, then we can just remove it. So we can approximate the ID curve as this. And what we want to know is VDS over ID. That's the on resistance. And it looks like this. This is also very frequently used one. For example, when we use transistor as a switch, those switches operate in linear region, and then we care about this on resistance. So this is also important. I suggest you to um, fully handwrite this equation and then get this formation. Next, what about saturation region MOSFET? Well, we use it a lot. I would say almost every analog block has a set of MOSFET that operates in saturation region. So this is very important. And then this is what we're gonna learn from our follow lectures. So here, you see that NMOS is connected like this, and then we're just applying the constant voltage here. And what happens is that this transistor, if this VDS is just sufficiently high, then the current is not changing that much. Even if we change VDS. So it turns out this kind of MOSFET usage is current source. This is like very well used circuit. Every amplifier has this. So again, current stays fixed even though we kind of move the voltage here. So you see again here, this MOSFET is in saturation region, and then this voltage is VDS. So here, this voltage, it doesn't matter if you change this voltage or something, the current just keep constant, like kind of constant. So it's a current source. And this is same for PMOS. Because PMOS source is sometimes connected to VDD, which is supply voltage, and then we apply them a constant voltage. And then the current from here is kind of fixed. They're not changing that much, even though the fluctuation in this node voltage. So we can say that as current source. I brought some interesting example from textbook because until now we plot the VDS and I curve. So we plot VDS and I curve, but we never saw VGS and VDS curve. We are not actually using this graph in like real design, but I think this is helpful for us to figure out the operation region. So first, V off, and it's starting from cutoff region. This is cutoff because VGS is less than VTH. Transistor is turned off. And this region, triode, see what happens. Triode region is, so this line corresponds to when VGS minus VTH equal to VDS. You see the point? So in lower area, VDS is lower than VGS minus VTH. So it's triode, and then opposite, saturation. You can take your time to understand this, and I highly recommend it to that you can be fully familiar with it. Okay, so we've been done on like most basic structure, operating regions, and then their current equation. Now let's look at the second order effects. It's kind of a side effect or maybe undesirable characteristic, but you know, nothing is ideal. MOSFET also has a lot of non-ideality, and those things are actually kind of a thing that we have to care when we design circuit. So there's a bunch of, and then let's look at each. Here's the outline of second order effects. Basically, MOSFET have all sorts of nasty second order effects, and that's what makes circuit design difficult. And that's also what makes circuit designer have their value, because it's difficult. Not many people can do it. We're gonna concentrate on these five. There's a lot more than this. Let's have a glimpse on it. Voltage limitations. We'll cover. We have to take care of this every tape out, and channel length modulation. This is an important thing. This is directly related to design stuff. Body effect, important. Subthreshold conduction. Well, it's good to know, but we're not that caring this much when we design it. Maybe now we care about it, but I mean, these things are more important. And capacitances. This also includes a parasitic capacitance. This is important, like when you design something like high speed circuit, or also something like stability things, but we'll figure it out. I mean, and then there's bunch more. First, voltage limitation. It means literally we cannot apply too high voltage on CMOS. So there's always a certain maximum voltage rating for a given process technology. For example, the max voltage in 28 nanometer CMOS is usually 1.2 volt, maybe kind of different, but around this area. The normal operating voltage would be 1 volt, but over the 1.2 volt, like literally the CMOS will break down because high VGS breaks down the gate oxide. So the high voltage, what we care about is like high voltage on gate. Drain or source, they can endure more voltage, but this gate voltage is a kind of very sensitive. And then here, this is what I've done in Apple. This is SOA test. I think every semiconductor company is doing it. It's like a safe operating area. It means once you made a like circuit, and there is some program that checked every node voltage. So it's like you operate the circuit. This is everything is in simulation. Operate the circuit, and then the tool check is there any point that exceeds the maximum voltage. This is very important because once you make a chip, and if some of the chip has like a this dangerous point, then it will break down the chip eventually, and it will cause a lot of loss in terms of money, right? Like recall or something. So anyway, voltage limitation is a really important thing especially for industry. So channel length modulation, this is very important thing. What it means is as VDS increases in saturation, as VDS increases, depletion region of drain substrate junction expands. What it means is here, this area increases. Like this is depletion region, and then it expands, and so this channel, the length of channel decreases. So here's L effective, and then the current is a function of the inverse function of L effective, so the current increases. So the point here is that even if the MOSFET is in saturation region, still the current increases when VDS increases. And that's from channel length modulation. Usually we don't want that. Usually we want the current of MOSFET just staying, even though VDS increases, but that's not the case. In real case, if you increase VDS, then current increases. Let's talk about more graph and equation. This is what what happens when they have channel length modulation. So what we suppose, ideally, in saturation region, the current is not increasing over VDS, but that's not the case in real life. In real life, we increase VDS, current is increasing because of channel length modulation. So error in IDE is approximately as linearly related to VDS. So what it means is here, this is the actual equation. In here, this is a saturation region current equation. Do you see any VDS related term? No, there's no VDS related term. So this equation is independent of VDS. But in reality, because of channel length modulation, we have to add this term, VDS term. So in this equation, if you increase VDS, the current is increasing. And then one thing very important, the important message here is that this is channel length modulation, which means in the previous slide, the current increases because of L effective. So because L effective means reduce the actual length of channel, and that happens because of pinch off. So the L changes compared to its original L. What if we have large L? What if we have longer L? That variation of L effective is less. I mean, in terms of percentage. If we have longer length, we will have less percentage of L change. Meaning that if we have longer length device, channel length modulation is not that much. So that's why, and then we talked before that we can use MOSFET as like current source, right? But for current source, what we want is that current is not changing, no, regardless of VDS. But because of channel length modulation, that's not the case. So here, the message that we can get is if we use longer MOSFET, that means it's good for current source. We'll cover that later. It's okay. You don't have to fully understand at this moment. But what says the message in this slide is that due to channel length modulation, we have to consider length in designing circuit. That's the key point. And here I also put some interesting figure. If we read it, it's like basically what it means is that as our technology, the semiconductor technology improved, the profile is getting far away from the equation. It has more like variation, imperfection or something. So in short, as technology getting advanced, we need more elaborate equation to model that, which means it's harder and harder to use equation when you design circuit. So we need a lot of simulation. Another channel length modulation slide, because this is important. How about comparing this L1 and L2? This is what we talked before. In ID curve, the equation looks like this, and then the like a derivation. So derivation of a current over VDS is actually, you can just actually do a derivative, then it looks like this. And then this lambda is kind of a channel length modulation parameter. And that lambda is also inversely proportional to L2. So you see that? What happens is that the slope here becomes 1 over L squared. So it means the slope becomes like flat, more flatter. You see what I mean? But so one can think, oh, if we increase L like double, then it helps, it makes the current flatter by 4 times. No, that's not true. Our comparison is that we want to make current the same, right? So if we increase L like double, we also have to increase W. So it becomes double, and then it turns out slope becomes actually 1 over 2. You see what I mean? So because we have to set the current as a constant, so if we have to increase it, so it looks like this. But still it's better. If you increase length twice, then we will get a double, like half flat current. Now the body effect. This is also called as back gate effect. Earlier, we assumed that the source, this is MOS by the way, the source here and substrate here were both connected to ground. You see? So here the source and bulk has the same potential, which is 0 voltage. But what happens? If the substrate or N-wall in PMOS, substrate is more negative than the source, well, positive in PMOS. So it's like this. So what happens if we connect this bulk less than 0, which means less than the source voltage? So here's what happened. More holes attracted to P substrate in this area. So in this area, more holes attracted to substrate because the polarity of holes is positive. And then we make P substrate more negative. So P substrate is kind of attracting those holes. So you see there's like larger negative charge behind, which is, this is a depletion region. Depletion region increases. So when you compare this here, when we connect the P substrate to ground, let's say just one line of negative charge behind. But since we decrease the P substrate voltage, this P substrate becomes more negative, and then they attract more holes from here. So the negative charge left more. Well, what the gates should do is they have to increase voltage more to mirror this QD. That's the point when the inverse layer happens. I mean, inversion layer happens, and then channel can form. So what I mean is that the VG has to be high enough to mirror all this left minus charge. So since this left minus charge increases, VG has to be higher. So VTH is increasing with this body effect. And then here's the equation. Just focus on this VSV. Source to bulk voltage, source to bulk body voltage. Now this is positive because source is higher than bulk. So this is positive added to VTH, so VTH increases. We also call this as backgate effect because it's kind of sort of works like a second gate underneath the channel. So that's why we called it as a backgate effect. It's kind of bothering this gate. So just tell them that like you gotta do you gotta have higher potential because I'm bothering you. So it's kind of backgate effect. Again, you see the point here. If the body voltage decreases, I mean it's lower than source voltage, VTH increases. That's the key point. Let's look at some example of how body effect can affect the circuit. So this one, source follower, very basic circuit. People use it like we use it for maybe like level shifter or some like impedance change. Oh, anyway, this is a very popular circuit. And then let's see how it works. We will learn it later. I mean, in next lecture. But assuming that we increase V in, but you see this one, this is a key point here. They have a current source, so the current has to be a constant. And then what happened to V out? If V in increases, because of this equation, V out should increase too. So it's kind of a like a linear, just constant offset is here, but when we ignore body effect. But now we learn that there's body effect in real life. So what happens here is that V out is just increase. But if V out increase, what happens? VSV increases, right? Because V out is VS. So if V out increases, VSV increases, and what happened? VTH increases, right? If VTH increases, V out can't follow fully. So it is supposed to be the circuit intention is supposed to be we are supposed to follow V in perfectly, linearly, with only offset voltage. But in reality, because of body effect, V out can't follow V in perfectly. You can also I will cover this in our in-person class, but I recommend you to understand it fully by using this equation. The point here is that body effect is bad. Well, some circuit use body effect, like in very particular case, but most of the time, when we design analog circuit, body effect is not desirable. So, is there any way that we can avoid body effect? Yes, we have. For example, this PMOS. PMOS is on top of inside N well. So this is P substrate, P sub, and here N well. So the way how we make PMOS is in P sub we dope N well on top of it, and then like source and drain is made with P plus. So what we do is tie this source and bulk, I mean body, in the same voltage. So VSB is always 0 and we don't see any VTH change. Here's an exercise. Please draw MOSFET symbol that represents this setup here. We'll talk about it in in-person class too. Anyway, PMOS has some advantage because like this, so it's kind of easy to avoid body effect. NMOS is harder because to remove this body effect in NMOS, we have to change the voltage of P substrate, but P substrate is like a whole plate. In PMOS, we already have our own isolated body, but in NMOS, they don't. But there is a special NMOS that we can do. We can remove this body effect. Maybe we can talk about it in person class 2. Here's the other second order effect for MOSFET, sub-threshold conduction. And as I said, as a circuit designer, we usually don't like this second order effect. This sub-threshold conduction also we don't want it. We don't like this. Here, up until now, we have assumed that a transistor is off when VGS is lower than VTH. This is not true. Some drain current does flow, like with this exponential thing. It's kind of a NPN junction or something like that. It's, I think, the detail of this equation, it's okay. If you're interested in, please refer to textbook. But here's what we can see. This is temperature dependent. Um, so this is kind of leakage. When we turn off MOSFET, we don't want any current flow, but there is current flow. It's undesirable, and we call that a leakage current, which is as I said, unintended current. So if we increase temperature, um, this current increases. For example, like when you design circuit, we simulate circuit in all kinds of corner, and then there's kind of a worst case simulation corner. At that point, um, we kind of assign them a very high temperature. It can be like 100 temperature, 100 degree. But that's it. This is simulation. Again, when in company, when we test, when we simulate the circuit, we check, we simulate them in all kinds of condition, and one of them is very high temperature. And in that high temperature, one of the key factor that we see is a leakage current, because the leakage current is maximum when temperature is high. And you know, high temperature happens a lot. Like when you operate, like you see that, right? When you use your phone a lot, and then the phone becomes hot, and that's when the battery consumption is increasing, and then because of the leakage and um, maybe other operation too. But anyway, this subthreshold conduction is leakage current, and then if temperature goes up, the leakage current goes up. And then for a circuit designer in industry, we care about that a lot. And also the other thing, um, like it also depends on VGS. As I said, let's say like VTH is 500 millivolts. Just assuming that. What it says is that if VGS is 100 millivolt, that's under VTH, but still there is a current, right? Because of the subthreshold conduction. But if we increase the VGS from let's say 100 millivolt to 100 millivolt, then leakage current increase 10 times. I mean, roughly, it's it's roughly 80. Well, it depends on technology, but this order. But you say this is still like, let's say VTH is uh, 0.5 volt. So both of them still are below VTH, but there is subthreshold conduction. So both of them still flow currents, and then their currents vary different like 10 times. And again, this is a digital circuit leakage current. This is huge actually. Um, in chip design, there is kind of a limitation, I mean, a spec that, oh, your leakage current should be lower than this or something. And then to achieve that, we simulate the circuit in very high temperature. The next side effect is short channel effects. What it is that if we make channel length, so you know this is channel length L, right? If you make channel length too short, there's kind of a interruption between in depletion region, and what happens is suddenly. So again, VTH, that's V-gate job. So V-gate try to mirror the depletion region charge to make inversion layer, which is channel. So it's more like V-gates try hard to like flow current. But if channel length becomes too short, suddenly VS, source and drain, kind of interrupt them. I interrupt VG and then, oh, I'm gonna do something too. So suddenly source and drain helps V8 too, because they're kind of like overlapped, because they're very close. What happens is VTH decreases. So here, as channel length decreases, VTH also decreases. That's the point here. Um, is it good? It's usually bad because this is not what we expected. We also want to control VTH. Again, one might think, oh, VTH is kind of hurdle. It's kind of obstacle. What if we make VTH really small? No, we need VTH. As I said in previous slide, if VTH is too low, there can be too much leakage current, and also a lot of some circuit need higher VTH or some circuit need lower VTH. It really depends on circuit application. So this short channel effect is not good because it bothers, it annoys the preset VTH value. So here's the MOSFET large signal summary. Suddenly we see this large signal. I think this is the first time to see this large signal term, but we will see in next lecture because we'll learn about small signal model. So anyway, we call this as large signal model. There's three regions. First one is cutoff when VGS is smaller than VTH, and current is like this because this is subthreshold region. It's kind of leakage. And here it shows that increasing temperature will increase this current. Next, linear region. Finally, VGS becomes larger than VTH, so inversion layer, this electron channel forms, and then current starts to flow. I mean, flow more than this. And in linear region, the trait is VD8 is not that high. VD8 is not high enough, so we don't see any pinch off point here. That's a linear region, and then the linear region current looks like this. We learned how to calculate it, and I recommend to remember this equation. This equation, it's okay. It's of course it's better for you to remember it, but we don't really use it when we design things. But this one, very very common to use, so please remember it, memorize it. And here the last region is saturation region. This is also VG, and assuming the VGS is larger than VTH, which means we already have inversion layer, which is we already have channel. The MOSFET is already turned on. And the second condition is VDS. Here VDS is larger than this value. So in saturation region, we see a pinch off point, and then we see this depletion region that kind of empty, and then our channel looks like this triangle. And we call this a saturation region because even if we increase VDS, the current is not increasing that much. Current is saturated. But we learned that there is a channel length modulation, which means because of channel length modulation, if we increase VDS, current increases, but not that much. And also we learned about like body effect here. That means if we increase the VSB, well, for example, like if we connect bulk to negative, then VS, then VTH increases. We also call this as backgate effect. Now let's look into the different story, MOSFET layout. Layout is like literally layout. We draw MOSFET. You see, this is kind of a MOSFET. So we call this a schematic. These are like a symbol. This is not actually looks like. It's not the physical look. What actually, when we see the silicon die, they actually looks like this. This is when we see the chip with microscope, they actually looks like this. And you see here, the key parameter will be width, length, And this is channel area and gate here. And then you see this black via like contact. This is, we call this as via, and we used it for like connecting metal on top of it. Because if we have this kind of transistor, we need to connect them to each others, right? And the way how we connect them, we also call that as wiring, is we put a like via here, and then we connect some metal from here. So, and then it goes to the other routing. This is actually what we draw. So the way how it works is circuit design first, and then we draw them in this real physical world. And then this drawing goes to TSMC or Samsung, whatever fabrication factory. Anyway, this is how it looks like. It's good to know about it. If you're working in circuit industry, you will see this a lot. There are tons of design rules. It means that you can't draw by on like whatever you like. There's a lot of like limitation. For example, um, you cannot make this length too small, or you cannot make this length too large. I mean, too long, too small, it's not. And then, for example, you cannot make this space between this contact too short, or you cannot make this contact in like different looking. Most of the process, they just let you draw in a single shape of via. So there's tons of rules. Like for example, this you see this contact and then this poly space. That's also there's a rule. So when we do tape out, we run DRC. It's a design rule check simulation. Not a simulation, DRC run. Um, Basically, there's tons of rules to draw. And one thing is that there's several things that I want to just mention. Number of contacts is important, which means that this one, because each contact has their own resistance. And then if the routing resistance is too high, then it's not good. So most of the time we try to use multiple this contact via. And then also we want to minimize the junction area. We will cover it today actually. And then, well, so many things to consider. Like for example here, this circuit actually looks like this. If you're interested in, you can just kind of mapping them. The next one is MOSFET capacitance, but we will stop the lecture here because of the time. Let's cover this in the next lecture. But just briefly introduce, this is NMOS, and then there's tons of like parasitic capacitance. Like between every port, there's every capacitors. And then this is how it looks like. And well, here most caps are nonlinear. It means that Q equal CV, right? It means that C is not constant. This is not constant. When we change V, C changes. That's what they call nonlinear. It's like here. We say V and then Q. In ideal capacitor, it just goes straight line because C is constant. But what they say nonlinear means it's not like this. It's not a straight line because C varies. That's what it means. So all of these capacitors are not linear. So when we kind of design circuit, we estimate each capacitor in kind of a small region. That's because I think we will cover the small signal model for MOSFET in the next lecture. So yeah, we're estimating the cap this parasitic capacitance in linear small region. Oh, thanks for listening to this class, and see you soon.